So we're going to talk about that homework at the end of the lecture today. And a fair warning that the clustering homework has been split in two parts. You only see in part A. There will be a part B that has to do the hierarchical clustering and BP scan. That's not so hard, so probably that's just 1 week because there's 2 exercises. Both programming for those 2, I think it's significantly easier than the K-means and especially the Gaussian mixture. How many people have looked at homework 2? Like read the homework, okay? So the fun part in homework 2 is that while the theory is beautiful, the practice doesn't really work that way, okay? Especially for Gaussian mixtures. So you guys are gonna have a hard time with that, I can tell you right now. In short. So we're gonna keep doing a little bit of theory today, and then my PhD student is gonna come. He's gonna show you a little bit about Gaussian mixtures. And we're gonna have a more practical discussion about what's up with those mixtures, especially for the data sets you have them for, and how Gaussian mixtures look really good on paper, but why they become so unusable in high dimensional data. So that's what we're gonna do now for a little while before we show some. I connect back the projector in my laptop. So I'm almost finishing it in these notes. I think by the end of the day today, let's say, I'm gonna have them online. Those are the notes you should use for Gaussian mixtures. But you can use any notes. I'm saying these are the ones corresponding now to notation we've done in class. So it'll be easier to know all the pi's and all the W's and all that. Oh. My main purpose for today is, while we're going to do more math here, is to really make sure you guys understand the concepts, the main concepts, one of them being likelihood, the other one being taking derivatives and setting up the parameters for one. That happens in a lot of data science, whether it's EM or boosting or neural networks. There's an objective, gets differentiated, and then things gets optimized based on it. So let's put that again here. Where was it? First of all, the normal formula. So this is a data point. It's a d by 1 vector. This is a mean, Gaussian mean, right? Sigma. So this is a d by d. And this is also d by 1. This mu is in the same space like the vectors. This is the same from last time. We had square root of 2 pi at power 1 over 30. So this is determinant. Is the sigma matrix within those bars. And then an exponential of minus 1 over 2 x minus mu transpose minus 1. X of means the same as E at that power, right? So I know we went kind of quickly with this, and we can also write down the likelihood, just to have a quick recap. I want you guys to go back to the notes and see if this is the expected likelihood. I'm going to write it here. Expected log likelihood So expected is with respect to, you guys need those acronyms, with respect to, when I say expected, I'm implying that something is random, right? If I say expected age in this class, why is it expected? What's random? Every time you hear the word expected, means something is not deterministic. Something it could be averaged over many possible values or many instances. Something. When I say expected age in this classroom, why is it expected? Why is not exact?
Because you don't know the age.
Because every one of you have different ages, right? So my wife's keep calling me. She knows I'm in class. I wonder what's in her head right now. Expected, no likelihood. Expected with respect to what? When I say expected here, I'm saying what? There's a random variables, remember, membership? We don't know what data point came from what Gaussian or what component. So we say that was what, pi I k, right? That was either 1 when the data point I came from component k, or 0 if it didn't. And we're never going to know that because, like we said last time, we have something like heights or ages, and we cannot map a value directly to a component, but we know probability for it. So the word expected comes from that it's going to have to be some sort of average based on those probabilities. And the log likelihood, there's a likelihood function to which I take the logs to make it more usable mathematically, right? So what was the formula? Was sum for all data points, sum of all components. We had this pi I k here of log of the probability of what is x one. What else we have here? We have Gaussian components. That's what we have. This was the mixture. So the other part that we need to have here is we have one normal, but when we have a mixture of k normal, a mixture of Gaussians, that looks like f of x. I think it's called the p of x. Is a sum over wk x mu k. Okay? So those are kind of the concepts we were dealing with last time. We were saying we have a function and we manipulated a little bit those logs. There was a case at some point with a log of a sum versus the sum of the logs. And we're saying we're going to use the sum of the logs because that's easy, but that's really a lower bound to the actual objective because the sum of the logs is smaller than the log of a sum. So if we maximize this, we're at least pushing the lower bound up. So we're pushing the real function up. Who remembers that conversation? Okay. So now we're going to have to add a few details to this. We did some last time. We do the rest today. First of all, I want to talk about this expression in high dimensions. I know we said already why is it so analogous to the expression in one dimension. Most of you have seen the Gaussian function one dimension, right? It's 2 pi, d is 1. Sigma is the variance, right? Which is just a number, right? So that would be what? Square root of sigma? Sigma squared as it is. The variance is sigma alone is the standard deviation. Sigma squared is the variance. Right? E at minus 1. This is x minus mu, right? Times x minus mu, that's squared. And then divided by sigma squared. Okay. So that's, we've seen that. But what happens, I wanna to call it practical considerations. For large D. So what happens with this when D becomes big? Now I don't want to say how big, it depends on several things, but certainly we think 784, like those images, it's already very big, not to mention 100,000 dimensions from words. Right? So there will be some problems with this when you run it for homework too. In fact, it won't work. And because of that, counting on the fact that you haven't already do it, I'm going to change the data set to here. The ones that's there says doesn't work, and there'll be another one that says, okay, this one works. The essential part being smaller d. So what are the problems with this? What do you think? Let's make some guesses. D is large as in 700 or 1,000. There's some problems here and some problems here. Do you guys remember what was there was a formula that computed this PIK, the probability. So this is the probability that xi belongs, let's write it in English, belongs to component. So that was some sort of proportion. How big is that value for component k normalized? So that's essentially wk times that's normal function of xi given that mean and that Gaussian. So that's the probability, the Gaussian probability. I'm going to say here normalized. Normalized saying if I have 3 components, that's the value for component, say 2 or 3, one of them, divide by the sum. Right? So every one of these functions is a sum of them. So this is normalized means divide by f of x, which is the sum of those two things. This is, say, the first Gaussian divided by the sum of how many I have. So one problem here is that for large D, sigma can have small eigenvalues. We're going to have to recap those. We're going to start a recap of linear algebra next time. Linear eigenvalues are some principal characteristics, if you want, of a matrix, and there's many of them. Typically, if a matrix is d by d, like our covariance matrix, there are d eigenvalues to it. So when d is large, there is a good chance that some of these eigenvalues are small. So that has several implications. One implication is that the determinant of d could be small or close to 0. Everybody knows the relationship between eigenvalues and determinant? High school linear algebra. The determinant is? Okay, so we definitely need a recap of linear algebra. The determinant is the product of the eigenvalues, right? This is the determinant, which is the product of eigenvalues. We're going to need this for our next module anyway, which is dimensionality reduction. And in there, we're going to have to very explicitly work with eigenvalues and eigenvectors. PCA, right? We're going to have to do that. The other problem with sigma having small eigenvalues is what happens here. The inverse, we're going to use a mathematical term, could be very unstable. Unstable in mathematics have to do with small changes in the input that produce big changes in the output. So when the matrix starts having very, very close values to 0, you can change a little bit the value, and the inverse, or 1 over the determinant inverse, becomes unstable. It can go to infinity, right? You can think of a very, very simple matrix. Think of the matrix just 2 by 2, right? Say this is A11, or let's call it sigma 1, 1, sigma 1, 2, sigma 2, 1, sigma 2, 2. So this is 2 by 2. Assuming I'm only looking at the main diagonal here. So let's assume I have 0 and 0 or outside the diagonal to make it really simple. If one of those things become close to 0, so if this is 0 here, what's the inverse of this thing? Diagonal matrices are very, very easy to inverse, right? What's the inverse? It's the inverses of each element, right? So this would be the sigma 1, 1. That's a number at -1. Let's write it explicitly as a number. So whenever you invert the diagonal matrix, you just take the inverse of the diagonal elements. But even in this case, you can see that if one of those is close to 0, the corresponding inverse element goes to plus or minus infinity. Very unstable, right? I can make a small change here, take a big change there. In mathematics, in theory, stability is not an issue. Mathematics can say as long as it's not crystal 0, it's fine with me. But in practice, on all data problems, you want to be aware of stepping into stability territory. Like you want to impose some sort of constraints that don't let you go into these oscillations from plus infinity to minus infinity with small changes. That's critical for data science. Every time you get into a stability issue or you get something unstable, it means that in practice you probably don't have enough data to really model what's going on in there. So there's no point trying to model plus infinity or minus infinity. You can just assume some sort of average until you get more data to do that estimation properly. So mathematically speaking, you want to avoid very high or very low values. But there's another more subtle issue here. So assuming you follow me, you're going to have to do this. One of your exercises in homework 2 asks you to implement Gaussian mixture for 2 by 2 and 3 by 3 matrices. So you're going to have to work with an actual matrix that's 2 by 2 or 3 by 3. The other exercise, you can use a library that we use many dimensions. But for the, I think it's exercise number 3, you'd have to actually invert the matrices. You can still call MATLAB or Java or Python functions to do this. But the main EM code, you have to write the main EM loop, you have to write yourself. Now, the data is very easy. You have to do this for a toyish data set that has been generated from Gaussians. So it's going to work like a glove. In fact, it won't matter how you initialize it. You're going to get those results for sure if you do the right update steps. When we teach the machine learning class, every single student got exactly the same mu's and sigmas, which are provided for you, by the way. That's what you should get, because those are generating mu's and sigma for the data. But you have to put your hands in the mud with these matrices, right? And people use this approximation a lot, by the way. So this is called the diagonal approximation. Saying, yeah, it's true, I have a D by D matrix, but for simplicity, I'm just going to assume it's 0 except for the main diagonal. So when you hear the term a diagonal covariance matrix, that's saying I'm assuming everything else is 0 than the main diagonal. Okay. So I want to talk a little bit about covariance matrices, so we all know what they are in a little bit. But the other issue that I want to point out, so I'm here at practical considerants for large D. I want to look at this exponential, right? Part of the Gaussian. If I look at this formula here, this is essentially, I'm going to say, this is kind of like the proportion of the kth component in mixture. I'm writing in English. This is the kth component of the mixture, right? Divided by the total. This is what really this expected pi k is, the membership, the soft membership, say 75%. It's saying that if you look at, you have 5 components, you compute those values, the overall mixture is the sum of them. You compute those 5 WK times the normal. If one is 75% of the total, the other 4 are adding up to the 25%. How many people follow me? Hands up so I can see them. Okay. So we're looking at this proportion. But this proportion, and I'm using English being sacrifice some rigorously here for intuition. This is an exponential function. So some argument, divide, normalize. Right? Because it's true that it's being multiplied with a weight, and it's true that there is some coefficient in front of it, the 1 over sigma, da 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 da. But the main juice of this function is really exponential, right? So the trouble with exponential function, I'm going to add something in here that says there is a function of x, right? Part of this is some x. I have an x in here, which is the actual data point. So I'm going to say it's like approximatively inside the exponential, it's x minus mu squared. Some other terms in there. So I'm now really bad at mathematics. I'm sacrificing a lot of mathematical rigidity to make a point here. So don't quote me on this, on any math-related stuff. This is an exponential that's quadratic in the input. True, there's some other fractions, sigmas, and what else, but exponentials are very fast functions, even without being quadratic. Imagine when the input is quadratic, right? Exponentials, with this base e, they are already quite fast. If your input is quadratic in there, this means what? It means small changes in x can cause big changes in pi ik, which is what I'm trying to compute here. My point is that this function can react extremely aggressive to small variations in the input. Yes?
What if x and mu are really close to each other?
Even if they're close, mu you can think of mu for this purpose as being fixed for now, because we are in the E step. So in the E step, we're computing the memberships, right? The M step deals with updating mu's and sigmas and w's. So let's assume for now in the E step, we have what? Mu's, sigmas, and w's are fixed. So in the E step, we're computing the memberships. This mu is fixed, but x is a variable from data point to data point, right? And k is a variable from component to component. The problem I'm trying to say here is I'm trying to convince you guys that for a large D, right? So for a large D, let's make this a little better. That's not me, right? Somebody else. Let's actually write this better. So I'm going to put this approximative sign because I don't want to compute the whole formula. But I want to talk a little bit about what is this times this. So ignoring the matrix. So let's put the matrix in then. Sigma minus 1. Who is, so that's sigma, the covariance matrix. Who is this x mu times x mu? I'm going to ignore the matrix. What is this? This is, if I write it down explicitly, is what? It's a sum. Right? So this is a sum here. Don't confuse the sigma with the sum. So this is the covariance. And this is a sum over, how do you compute a vector versus times another vector? You go over all the components, right? How many components I have there? That's not the mixture components. These are the vector features, right? I have D, so let's say D or T equal 1 to D of some X I T here minus mu I T, right? Something like that. It's gonna be a square thing because it's multiplied with Now this is not correct. I want to be very clear, especially this movie going on YouTube. I'm a little worried that somebody will say, hey, the covariance matrix doesn't go in front of the sum here. It doesn't work like that. True. So that's why I have a big approximative sign. I care about intuition here, not the actual math. So here's my point. This covariance matrix may do something for me, maybe not. Although I already said there's a problem with sigma minus 1. In many dimensions, if one of the eigenvalues is small, sigma minus 1 itself could have large values, right? I said this here. If one of these values is small, 1 over it could be very high, and then the whole thing gets messed up. But even without that sigma, what happens if I have many dimensions, if I have 1,000 dimensions? What's going to happen with those sums? Are they likely to go where?
So in this particular equation, why you're looking at the negative sign, which on the exponent, so it's minus 1.
We miss a minus here? Yeah. Minus. Is that what you mean, the minus here?
Yes, the exponent would make the bigger changes against small changes.
What?
So even if the x is large, the power minus x would.
Right, so the minus will have the effect that 1 over this, that's your point, right? 1 over becomes closer to. So if this value is big, he's saying if this value is small, this value is big, right? So this value is 10,000 minus 10,000 drives the exponential towards 0. Okay? But what happens to the sum here? When D gets bigger, the sum has more things to sum up, right? So that's another problem, that even though the centroids could be closer, I mean, many dimensions will allow me to have more control on the centroids, the sums themselves become bigger. Although, again, this is not exactly that formula, because the stigmas doesn't come in the front of it. So isn't it true that this implies I have to think of his comment, what's going on here if I have more dimensions with the big values? How do they change things? Our experiments for Gaussian mixtures have the problem, the biggest problem that you're going to have, I think, too, is that this has this effect here that small variations, which are happening because you have 60,000 data points or something, small variations produce big changes, and big changes will cause the proportion to be very skewed. So I'm going to add here very skewed, meaning they almost hard k-means. So hard k-means means what we notice for large D is that those pi k come up being close to 1 or 0. If I look at those values, the one that I'm normalizing here, before normalizations, they're so different. One of them is so much bigger than the others that when I do normalization, that one becomes a 1, the rest become all zeros. Now, it's possible that we have a bug in our code, and when you guys do this, it works out magically. Let's see. So far, we couldn't control this large D Gaussian mixture to act anywhere different than the hard k means. I have to think more about this question that he's asking, how this minus affects things. So that's a good question. Maybe we can come up with an answer.
I think because even the exponential is very small, but you normalize it. So
You mean here,
the denominator also very small.
this?
Yeah, because the denominator is the sum up of the denominator.
Right. So I'm not talking about, you're talking about this normalization?
Yeah, I mean.
I'm talking about the difference in these values. If I just compute the WK times the normal before normalization, if one value is, I don't know, say 0.7, and all the others are very, very close to 0, then what I'm going to get is that one at normalization becomes 1, and the rest becomes 0, right? So I don't think we should worry about normalization. My worry is that this is a very sensitive, if you like, function. Sensitive means unstable, that we cannot control the pi's, the WK times this, to be relatively close to each other. We cannot get 20%, 30%, 50%.
Yeah, because in practically when I do the program, the denominator is very small when the D is very high. But after normalize, like
one of the values becomes very high,
yeah.
and everything becomes very small.
Yeah.
That's because if you look at the output, they're all very small, like he's implying. So one is, E at -7. That's like having 6 zeros after the decimal. But the other ones are E at -12. So compared to the E at -7, they are extremely small. So after normalization, only one pi becomes 1. Again, maybe we have some bugs in our code. I doubt it. But the problem we have so far in large dimensions is that those pi's always come out as hard pi's 1 or 0, which clearly negates the whole point of a mixture. Right? I mean, we know how to do k-means on these data sets, so we don't want to do that. So that's something we're going to show today in class as a demo, what's going on there. And we believe it's a pure function of the dimensionality. So as an exercise, your homework 3 is going to say, reduce the dimensionality of the data. Instead of 784 dimensions, use only 20. Now the data is not as accurate representing 20 dimensions as in 784, but then I think that the Gaussian mixture will work much better on 20 dimensions than it works on 800 dimensions. Okay, so now with this discussion, I would like to do a recap of what covariance is. Just very brief here. So I have two random variables. I'm going to call them xi and xj. What is the covariance between xi and xj? The reason I'm putting those i's and j at the up and not down is because when I write the feature matrix, typically the down exponents are the data indices, the first data point, second data point, third data point, and the upper exponents are the feature columns, right? So this is if you want to read it this way, this is column I versus column J. So what is the formula here? xi minus mu I. So mu I is of course the expected value of xi, and mu j the expected value of xj. So this is like expected value of xi minus expected value of xi times xj minus expected value of xj. So that's for two variables, right? I have two variables, you can think of them, so I have many data points. Xi could be the age, and xj could be the weight. Right? So this is how you have to think about it. I have a data set, this is x1, x2, xn, if I have n data points. And what I call xi is the height of the people, and xj might be the salary. So these are two columns in the data. That's how I usually imagine the data when I think about it. When I say xi and xj this way, I'm taking two columns here, two random variables. These are observations for each variable. That's the covariance. Now, what is, from this formula, what is the variance of only one? How do I say, okay, as a particular case of this formula, what is the variance of one column? It's simply the covariance of that column against itself. Right? That should give us exactly the variance formula. Square. And if I am to play a little bit algebraically with this formula here, I have a thing, let's see if we can figure out where this is coming from. That's the expected of xi times xj minus mu I mu j. Is that true? If I open this parenthesis and I distribute the expectations, would I get this formula? Clearly there is an xi times xj in there, and that's the expected of xi xj. Mu I mu j is mu I times mu j, right? And the expected of that is that. Is it minus? But this is a plus here.
Two minus.
Right, so there's a calculation that you guys have to do. What's going to happen with xi times this? Maybe we should do that.
Yeah.
So I have xi minus mu I times xj minus mu j, right? Which is expected of xi xj, right? Minus expected of xi, this one, times mu j, minus the expected of mu I times xj, plus mu I mu j. Right? So this is expected of xi xj. How much is this? Mu j is coming out of this expectation, right? So this is mu I mu j, right? This is again expected of xj gives me mu j, and mu I is a common factor, so that's again mu I mu j plus mu I mu j. So now I have minus 2 oranges plus 1 orange. Get the expected value of xi xj minus mu I. Okay. That's something that's very useful to know in general, not just for this. So now I want to make another observation. When is this 0? How do I get covariance 0? When it to be 0, this has to be equal to that, right? So what does that mean? So if I say, I have to erase some parts here. If I say I want this covariance to be 0, that's equivalent to saying expected xi times xj has to be mu I times mu j, right?
Yeah.
Which is, in fact, expected of xi times expected of xj. So if the expectation of the product is the product of the expectations, means covariance is 0 between them. Means, is that implication in what direction goes? If this is true, they are independent, or if they are independent, this is true, or they're equivalent. So let's take it little by little. If this is true, does it mean they are independent? Not necessarily. But if they are independent, is this true? Yes. So this is not a two-way street. Okay, you have to make sure in which way you put that implication. If they're independent, this will happen. But if this happens, they're not necessarily independent. So now, how is this covariance matrix going to look as a big matrix? Suppose I really want to write down a covariance matrix. How is it going to look? I'm going to erase this to make some space here. I want a sigma covariance. It's going to be a matrix, right? And it's simply going to have that on every single ij, right? Ij. These are all the from 1 to d, and this is from 1 to d because the covariance is not like the feature matrix n by d, it's d by d. So what's going to be in here? This is the covariance between xi and xj, which is the expected of xi minus mu I times xj minus mu j. So that's the sigma that the Gaussians are using. It's a matrix 784 by 784 if you have images. And each one of them is the correlation or covariance between feature 2 and feature 7, if you have the value 2 and 7. Two more observations about this. Main diagonal is what? Is the variance of xi. On the diagonal, we have the actual variances of each feature. And if the sigma happens to be diagonal, remember what it means? It means it has some values on the diagonal, but everything else has 0. That's corresponding to what? Again, it's not a two-way street, right? That is true if the features are independent. Because independent features create 0 covariance, but the other way might be an accident. You can get the 0 covariance by accident, even if the features are not independent, depending on your data. Okay. So now I think we recap the Gaussian part and why I think there's some problems with high dimensions, but I would very much appreciate if you guys try it and tell me why, if it doesn't work, why you think it doesn't work. Our gut feeling is that this high D prevents this to work in any case. The other part that I want to do here is take this log likelihood What did we do last time with it? You remember? We were differentiating the delta how do we call this? Log likelihood? Expected log likelihood. So we are differentiating this xi, and we are saying given pi I k is 1 with respect to, which one did we do? I think we did with respect to mu k or mu n. And if we said that differential equals 0, we did some calculation last time, and we've got to the update on mu. That was mu k is the sum of pi I k xi divided by the sum of pi I k. That's of course over all i's. Do you remember this? We take a derivative, we set it to 0, and we averaged it over all the possible pi I k's. We had to put in the probabilities in. That's the average. And then this formula, I think, makes sense. If somebody shows you the formula without the derivation, I think it makes total sense. It's a weighted average of the data points. In k-means, it's simply an average of the data points that correspond to there, and it's a weighted average because each data point has a weighted average. I would like to do now, to try to do this for the sigmas. So in case we didn't have enough math last time, let's try another 10 minutes exercise. What happens if I differentiate these? But not with respect to the mu's, with respect to the sigmas. I think with respect to sigma at -1. Here's the formula I have here. So differential over differential with respect to sigma to -1 is logarithm of 1/2 exponential of -1/2. I think this is saying differentiate that. It's nothing fancy there. Okay, that's the derivation. Now, I think this is just saying we differentiate the one of the components there. So that's the Gaussian formula. How do we get here? So 1, 2, where do I get log of 1, 2 of this? So where is the 1, 2 coming from? I think the pi 2d, right, that goes away because it's kind of log breaks the product into a sum, and this is kind of a constant, so it goes away. With respect to a differential, with respect to sigma, right? The 2 pi d by 2 does not contain any sigma, the differential is 0. This became that. Does that make sense? So 1, 2 is the 1, 2, log is the log, but why is now sigma k at minus 1? I think that's just another way of saying the determinant, which is a value, the 1 over the determinant is the same as saying the determinant of the inverse of the matrix. Determinant of A at minus 1 is 1 over the determinant of A, right? Is that true? The determinant of A at minus 1 is 1 over the determinant of A. I think that's true. So I could have written the determinant at power minus 1. I think that's the same thing. So now in here, what's up with the exponential? 1/2 of this. So the log, I think the only thing that happened here, the log goes away with the exponential. So I didn't take any derivative yet. I just say log, exponential, the inverse to each other function, so I got that. Now what happens here, I think this comes from the derivative of the logarithm, right? Produces this term, and the derivative of this part produces this. There is a relationship that's being used. Two relations. So how do we get this? The relationship we need, it's a matrix differential. Let's call it M to be more clear. So that's what happened here. The derivative with respect to a matrix of log of the determinant of the matrix is M at minus 1 transpose. Now that you have to trust me. Not me, trust this guy who wrote those notes. We can find easily linear algebra derivatives. If you take a course in calculus after linear algebra, there is a chunk of the course that deals with derivatives of matrices. And it's not hard to prove these formulas. But if you didn't do it, it may feel quite hard to start. The other thing that happened here, the formula that's being applied here, is the derivative with respect to a matrix M of X transpose MX is X times X transpose. So of course M was being sigma at minus 1 here, the matrix which I take the differential with, and I had the X transpose times X, so the result is X times X transpose. I think the easiest way to see this is by applying the analogy from one dimension, right? If I have X times, say, some value M times X again, because X transpose is the same as X in one dimension. If I take the differential of this with respect to M, what do I get? It's X squared, right?
Yes.
So I think that's the easiest way to see this. Of course, there's a generalization in many dimensions. You can do the calculation, or you can trust me that it works. Okay, so now what do we want? We want this. So we want the sum here. This is for one data point, but we want the sum for all data points. Now we're bringing that pi k in times what we've got here. Okay, minus 1/2 xi minus mu k times xi minus mu k transpose. So now what I did from here to here was to say the sum over all I of this, which was the differential of the likelihood for one xi given pi im, pi I k. This is now averaged, expected of, is this one here, and I want it to be 0 because I'm setting the differential to 0. So what happens from here to here? Two things. I'm adding the probabilities. That's the same like before, because this was conditional in pi k equals 1. And I'm summing over all the x's because to compute those sigmas, the derivative is not just for one x, it's the sum over. Once you take the log likelihood, you get the sum over all the possible x's. So now I'm summing up to 0. I have to solve this equation. So let me put here the answer, and we can say if we figure out why that is. Is this true, that from this I get that? So think about what's going to happen with this. 1, 2, and 1, 2 goes away because I can just multiply with 2 and get a 0, right? Some of the pi k sigmas become one side, and some of the pi k's of this become the other side. So sigma becomes a common factor in that side. So you really have to think, I think the easiest way to, there's an intermediate step here that says sigma, the covariance matrix, times the sum of the pi I k, that's the sum over I, is the side on the other side, sum of the I of pi I k xi minus mu times xi minus mu transpose sum over all I pi I k xi minus mu k. So sigma k is a common factor here. And now, of course, if I divide with the sum of pi k's, I get my update formula. Ends up who's with me. I'm not going to require this. So we're not going to have an exam or quiz. This is required. But what I think you should know is that how is it possible somebody takes a likelihood, the log likelihood, and starts with derivatives and all that, and ends up with a formula like that. Now, you may not remember the steps, but you should know the procedure in principle. I can take the likelihood, differentiate with respect to mu's and sigma. Those are called parameters. In different problems, I may have different parameters. And then get an update formula. Now, does this make sense? If somebody just shows you the formula and say, hey, I will show you the derivation. What do you think? First of all, what happens in the hard K means, let's assume the pi's are 0, 1 for a second. What is this? This is kind of the covariance matrix, right? Isn't that exactly the covariance matrix? X minus mu's, X minus mu's. Of course, there's the mu k here is the k corresponds to the component. So if I have 784 dimensions and 3 components, I have 3 mu's. But every mu is on 784 dimensions. So if I do x minus mu times x minus mu as vectors, that's why one of them is transposed. Don't I get exactly the variance formula, covariance formula, the whole matrix? I do, right? So then, what's the point of these pi's? Why intuitively, what are the pi's doing inside my covariance formula? It's a weighting, right? It's saying the contribution of a certain data point xi, that's an observation, right? We compute variance or covariance, we go by the observations we have. And we have many covariance ij's, right? It's d by d. The contribution of a data point in this formula here, that's a patient or an image out of my collection of 70,000 images. This is the covariance for the second Gaussian, right? So I have 3 Gaussians, 784 dimensions, and 70,000 images, right? I'm computing the covariance for the second Gaussian, k equal 2. So the contribution of a particular image to this formula here, this is the covariance between what and what? Between the pixels, one pixel in the matrix versus another pixel in the matrix, right? So it's the same pixel. Pixel I is the pixel number 17, corresponds to some pixel in the image. Pixel J is the pixel number 346. You look at those images, 28 by 28, one pixel is here, the other one pixel is here, and the sum is over all the 70,000 images, right? Because 70,000 images may have some value for this pixel, some value for this other pixel. Now the question is, how much a particular image should contribute to this value? That's where the pi k comes into. That's saying it contributes a lot if pi I 2, because we said k equal 2, is likely that image comes from that component. It has a high probability for that component. And it contributes almost nothing. If pi k is close to 0, that image won't contribute nothing to that sum because it's not part of that Gaussian. So this is effectively doing the covariance formula, but weights each point according to how likely is that point has a mass on that Gaussian. I think that's very nice. I think this is saying that the covariance update comes naturally as a covariance matrix here. See, we didn't use it as a covariance matrix, we just took the derivatives here. And it just so happens that it comes up exactly as covariance. That's because the Gaussian and the likelihood and the covariance are more related than just what we said. There is a back loop of why those things are all related. So it's not an accident that the update formula recomputes the covariances, which are actually what controls the Gaussians, right? Which are actually how the likelihood is determined. There is a third update which you won't do, I mentioned last time, the update for W's. For these ones, you need something more than derivatives. You need something called Lagrangian multipliers because there's a constraint on the W's, and you have to account for that constraint. These details are in the notes here. The last thing I want to do is something I started last time as an exercise. I thought I'll spend 5 more minutes on that. It's still an exercise. So next time, we should move into some recapping of linear algebra. That's necessary for a bunch of things we're going to do next week. So last time I said I have a similar problem, although not with images and Gaussians. I have it with coins. So I have k coins with biases Q1, Q2, up to Qk. All those biases are of course in 0, 1. Those Qi is the probability that coin I comes head. So they're not the same. Some coin is fair 50-50, that means Q is 0.5, right? Some coin is heads all the time, maybe a coin that has heads on both sides, that'll be 100% heads. Right? So I'm generating now a sequence of n data points. Each data point, I'm going to call it xi, is, so each data point is pick a coin, let's say Cj. Actually, let's be consistent. Let's say K, so this will be K. Pick a coin, flip it D times. So my data point will be some sort of flip outcome, xi1, xi2, up to xid, right? And all of these values are either 0 or 1, right? Or typically tails correspond to 0 and heads correspond to 1. So heads or tails. So I pick a coin, flip it times, and I'm also counting in here for each data point yi is the number of heads. So I'm saying out of this, what's the number of heads, of course, will be the sum, right? Because these are 0, 1s, 1 indicating the heads. So if I go for e equal 1 to d of xi t, I'm summing up, I see how many heads I have in there, right? Now this is one data point, so I'm going to have another one, x2, another one, x3, all the way to xn. This is x3, 1, x3, 2, up to x3d. Now the coins I picked are hidden to me. So what is the corresponding pi I k here? It's a random variable right before. This is the data point xi used point ck. Right? So what I'm getting is this, but nobody tells me what coin has been used. Can I tell for sure what coin has been used here? No, because every coin could possibly generate this particular sequence. Now, some coins are more likely than others. If I see 0, 1, 0, 1, 0, 1, roughly the same number of heads and tails, that's more likely to be a coin with a bias Q, about half. But if I see a lot of heads, it's more likely to be one of the coins that has a higher bias, right? So the hidden information is the same like before, when we didn't know what group, what data set, what data point comes from. In here, we don't know for each row, which is a data point like before, what coin has been used to flip that, right? So what do I do next? Okay. So what will be the update rule? So suppose I run EM. I'm going to have a E step. It's like before. Given some parameters that I have, I'm going to compute the memberships, right? So who is pi ik? That's going to be like before. It's the WK probability of x I given to divide by the sum. So this is like before, except I don't have a normal here. I have a general probability. We'll talk about that in a second. Who's WK? Who was WK before? Right, the coefficient for the mixture, but what was the intuition of these coefficients? When WK is really big? When a lot of data points come from there, right? So in the M step, we're gonna have the WKs are gonna be the sum over pi IKs for all I. That's the sum of the memberships. Tells you how many times, in this case, it's how many times that coin has been used. Before was how many data points belong to the second Gaussian. And who else needs to be updated in the M step? In here, I don't have mu's and variances. The only parameter I have for each coin is what? So before I had mu's and sigmas for each component. In here I have the mixture coefficients just like before, but what I don't have mu's and sigmas for each component, each coin. Each coin is a component. I only have one parameter, the bias, right? So I have to recompute the bias. How do you think the bias is going to get recomputed? If I show you this, and I give you an estimate of memberships, think about hard memberships, not soft memberships, it's easier. So I tell you, this is coin 1, this is coin 2, coin 1 again, coin 3, coin 4, coin 1, okay? How would you determine the bias of coin 1? Estimate the bias of coin 1. You would look only at coin 1 and would do what? Average what? Number of heads you see, which is this y, right? Y is the number of heads you see. So you would be like, okay, this is the sum for all coins, for all data points of the yi times pi ik, right? Because you only want to do the ones for coin 1. And you will divide by how many times coin 1 shows up, which is pi ik. Now, of course, if I have soft memberships, I don't know pi ik, it's a random variable, it's either 0 or 1, but I know the probability of pi ik, right? It's like before. So it's a weighted average. If I know coin 1 happens here 30% of the time, 90% of the time, 10% of the times, I use those weights, I average the number of heads I see as a proportion, I say, what's the average proportion of heads? That's my estimate for the coin 1 bias. So see how EM can be applied in here. It's the same chicken and egg flipping between those two stages. The only difference in here, I'm going to let Cheng talk in a second, is this P. Who is, if I give you a sequence, what is the probability of observing that sequence? X is one of those, right? Given a particular bias. So if I tell you, this is the same concept like before, right? Just before we said we think it's a Gaussian. We think there is a mean, a central mean, and most of the data points would be around the mean. In here, we don't have to make that assumption. We know exactly how to calculate this for coins. If I tell you a coin has bias 70%, aka 70% chance to get heads and 30% chance to get tails. Now I flip the coin, I know exactly how many times I flip the coin. D times. What is the chance of observing that many? This is really the same probability. Turns out we want here. We don't want the exact sequence. The sequence itself is not telling us anything about the heads. The only thing we care in the sequence is number of heads, right? If somebody tells you estimate the heads, even though the sequence tells you heads, tail, 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 head, head, the sequence itself, it's irrelevant for the heads. So as far as we're concerned for bias, this we really want the probability of yi, right, given q, which is what's the chance of obtaining exactly that many heads. So we know how to do this exact. We don't have to make an assumption like Gaussian is an assumption. We think the data looks Gaussian because in nature it's Gaussian. For coins, we know exactly how to compute the probability that flipping, I'm going to write it in words, probability that a coin with bias Q, probability to obtain heads, flipped D times gives Y heads. So what is the probability that for coin with certain bias, flip D times, gives me exactly, I don't know, 5 heads? There is a specific distribution that does that. Bernoulli is to get one flip. No. It's Bernoulli to get one flip. If the chance of getting a head is what? It's going to be Q, right? And getting a tail is going to be? 1 minus Q. But what if I do it D times?
So 1 theta Q is to yi, 1 minus Q is to.
So this is, he's saying it's Q raised to Y, and 1 minus Q raised to D minus Y. And I have to add a bunch of sequencing counts, because now even if I get exactly Y heads, they could be arranged in my sequence in how many ways? I have D positions, and Y of them are heads. How many ways to arrange Y heads in D positions? D choose Y. So how is this distribution called? Now this is much better than the Gaussian because it's exact. We know coins will work that way. If assuming the flipping mechanism is fair, like I need to have some sort of, not induce some bias by the way I flip a coin, right? Assuming that the flips are independent and each one of them gives me Q probability of a head, that's exactly the distribution I should observe, no assumption. Okay, so now we're gonna ask Cheng to tell you something about your homework. You need the dongle? No. What? 20 minutes? Actually less. So yeah, I think there's a class right after. Yeah. It takes time to warm up.
Yeah, so last time we tried k-means on this Laplace data, and I show you that the training objective of k-means always improves as the training goes, right? If you remember, the training objective of k-means is the sum of distances between each point and the cluster. So this sum of distances should always go down as we proceed. That's an internal evaluation of how well your training algorithm works. If you get a good small sum of distances, that means your algorithm is working well. If you get a big one, that means your algorithm is not working well. So what asked me to show you another way of evaluating k-means, which is to use the external label that is available for this MNIST data. So if you remember, for each digit, we know the identity of the digit, whether that's a 1, 2, 3, or 4, right? So we can use that external label to evaluate the quality of the k-means. So intuitively, the clustering is good if all images that are assigned to the same cluster have the same digits. For example, if all images are digit 1 in a cluster, that means that clustering is good. If you get many different digits in the same cluster, that means the clustering is not working well. So this is called purity. I'm sure Porter has talked about this, right? Basically, you just check what's the most popular digit in your cluster. You treat that as a label for the whole cluster, and you say whether the label of each digit in that cluster aligns with the label of the whole cluster. Then you count how many images are correct and how many are incorrect. That's purity. Still working?
It's at you. No? Oh, no.
Okay. Now I'm gonna show you how the purity value on MNIST looks like. So this is the same procedure as before. We run k-means, and in each step we check which data point gets assigned to a different cluster and so on. We can also compute the internal objective, which is this sum of distances. So you can see the sum of distances always goes down. Okay, at the end of the algorithm, I also compute this purity value is 0.74. That means about 74% of the images belong to the correct cluster, meaning its own label agrees with the most popular label in that cluster. Here I'm using.
So what the TAs might ask you at the demo is to pick 2 random images from a cluster and to display them somehow, or to look at them to see, okay, at random, if I try this a few times, how related are the images, apart from the purity value. Purity is not very good. We talked about more interesting ways to do it with the entropy calculations. The book talks about that, but purity is a lot easier to compute. It's a majority divided by the total sort of thing. And Cheng showed you last time that if you look at the clusters, he has a centroid, and then what are other images in that cluster. Visual inspection, I think, is what the TAs are going to be looking for, apart from just a number.
Yeah, so the 0.74 purity I just got was achieved with 20 clusters. Now I just change the number of clusters to 10, and I rerun k-means. Now the purity becomes lower. It's now 0.56. So and make a guess of why the purity goes down. Or in other words, as we increase the number of clusters, do you expect the purity to go up or go down? Go up, right? Because as we use more and more clusters, each cluster can get better and better. Because in the extreme case, if we allocate 1 cluster for each data point, then each data point will be assigned to the cluster with the same label, right? Let's actually test this. Here I have only 100 data points, and I want to use 100 clusters and see whether the purity is 1 or not. Try. while to initialize 100 clusters because I'm using a fancy initialization algorithm. Yeah, sure, this one. So you can see as we increase the number of clusters, the purity number can go arbitrarily high. So it doesn't make sense to compare two cluster results if they have a different number of clusters. Right? So it only makes sense to fix the K first and then check purity. Okay, so this is the K-means. Next, I'm going to show Gaussian mixture.
So for Gaussian mixture, Cheng has, I think you have your own code, right?
Yeah.
But he also tried packages that do Gaussian mixtures. The one with the 2x2 matrix and 3x3 Toy data, I think that's easy. It's gonna take you guys a little while to figure out how to deal with the sigma -1 would be your biggest problem. But you call a pseudo inverse. We'll talk about that at office hours. It's gonna work. So far, the running a mixture on real data, something with many dimensions, has been problematic. And I think he succeeded on one data set, but not on another, right?
Right. So let me show you the Gaussian mixture on the artificial data very quickly. This is the simulation data generated by a mixture of 3 Gaussians, 2D picture, 2D Gaussian. You can see it's run very fast, and the log likelihood keeps going up. Right? Keeps going up, and those are the final Gaussian components. This is component 1, and it has a higher value of 0.3, around 0.3, and mean is around 7 and 4. And we have a covariance matrix. You can compare those numbers against the numbers released on the homework webpage. You should get almost identical numbers because it's very easy to train.
But how is this initialized?
Randomly. Yeah, this is very easy to convert. You can just initialize randomly. It will give you the right number in the end. Let me show you another data set. This is the spam data set. It has 57 features. It's a text data.
So this is not, we don't have the raw emails. We only have the processed features already into a feature matrix. Those are not unigram features. Those are extracted features that people thought they are relevant to spam, like was the word free or the word porn or the word something. Whatever people thought are relevant features to spam, they extracted it. There's about 57 dimensions of data. There's also labels, so there's labels whether each data point is spam or not spam, but that's not relevant for this mixture, the actual label.
Right, so Trini has to convert this group. I only let it run for 10 iterations. Maybe it can still improve a little bit if I ask it for a few more iterations, but you can roughly see the trend is the same, right? The log likelihood always goes up. Just different from the k-means objective where the sum of distances always goes down. Here you want to maximize the likelihood instead of minimizing. So you should expect these numbers to go up. If you ever see these numbers to go down, that means your implementation is buggy. You always see this kind of trend. And so here you may notice that the log likelihood is a very big positive number. So this is you compute a log likelihood for each instance, and you sum over all instances. So here roughly I have 5,000 instances. So on average, each instance has a log likelihood about a few hundred. That's log likelihood. That means the real probability is on the order of e to the power of a few hundred. That's a big number. So if you think about it, you may feel this is weird, right? How could the likelihood, the probability be e to the power of 500? How could this happen? Well, this happens because you are dealing with a density function in Gaussian mixture. So the density function in Gaussian mixture looks something like this. So this is not bounded. It's not between 0 and 1. It's not a real probability. This is the probability density, if you remember the definition. So don't be surprised if you get a big log likelihood. That's normal because because the density function is not bounded. It can go to positive infinity. So at the end of the training, I also print the mean of each Gaussian component and the log determinant of the covariance matrix of each Gaussian component. You can see log determinant is negative 193. That means the determinant itself is e to the power of minus 193. That's almost 0. So this part you have to deal with in your implementation if you want your Gaussian mixture to run on real data. You cannot really compute the determinant as in the definition of Gaussian distribution. You can see there's a determinant factor here. You cannot really compute this directly because you will get 0. If you get 0, you get dividing by 0 error, right? You have to compute log of.
I think it's very related to the argument we were talking about. Remember, he was asking what's up the minus in the exponent. You're saying the problem is really at the denominator, not at the numerator. Because
Right.
Right, I think we need a little bit more thinking about that. There's clearly a problem here. You see those numbers, when you take the log of something and you get 190, that was a huge number. So that causes the problem, but we need to think a little bit more whether the problem is inside the exponential or in the denominator. Cheng is pointing to the denominator, which is the determinant of sigma. I was saying something about the numerator being summed up over so many dimensions.
Right. You also need to deal with the numerator carefully, but I think that's probably easier to deal with. Basically, the inverse sigma can become unstable. For example, if you think about this MNIST data, basically you have 784 dimensions. Each dimension corresponds to the pixel values at some point, right? If you look at all the pictures in that data set, you will notice that the upper left corner is always black, right? So there's no variance for that dimension at all, right? So that means if you compute the covariance matrix directly from the data, you will have one element at the diagonal that is 0. Actually, you will have a whole row in the covariance matrix that is 0 because there's no variation for that pixel. So that means you cannot really inverse this matrix because this matrix does not have full rank. You have a row that is always 0. That means the matrix is not invertible. So you have to deal with such instability in your implementation. You cannot just follow the math, the algorithm, because the real data may not really match this Gaussian assumption. You have to add some trick to make it work. Basically, to deal with this degenerate case, you just add some small numbers along the diagonal. You say the elements along the diagonal should be at least 0.001, something like that. This will fix the numerator problem. For the denominator part, you will find a way to compute the log of the determinant directly instead of computing the determinant first, then the log. So you can check online, there are some discussions there. So this is the Gaussian mixture on the spam data set. You can see here I also print the gammas for a data point. You can see these data point is basically spread across two clusters, right? You see, the first cluster has a membership 0.5, and the third one has a membership also 0.5. So this means this is a clustering is soft instead of hard. So let's try Gaussian mixture on the fraction data set. This fraction is very similar to the MNIST one. You'll see a big difference here.
So this is the one that doesn't work, right?
Yeah, it doesn't work.
It's getting stuck at the first iteration. You can't make any progress, I think. Make some progress. See, now it's stuck. So Cheng, we gotta